Okay, welcome everyone. My name is Shahab Ardalan. I'm from IR Labs, and today we're going to talk about optical I/O chiplet for heterogeneous computing. Okay, I have two graphs here. Let's start with the first one at the left. At the x-axis, I do have the time in years, and then the y-axis is going to be the power. The blue dotted line here is going to show actually the power trend for total power per package. And the purple one is actually shows the trend for required power for driving out the data off of the chip or off of the package. And clearly here we are seeing that we are surpassing the limit, and this solution, this basically trend is not going to be basically sustainable. Either we have to reduce the power for I/O or have a better packaging. But how we can solve this, and where is basically the power trend for the I/O? Then switch to the basically right graph here. We do see actually three regions. One is for the I/O for in-package, one for onboard, and one for off-board. And the x-axis shows actually the reach, how much reach this I/O needs. And the left side is actually bandwidth density times energy efficiency of the existing solutions. And we see just going from the in-package to the onboard, we are losing 4 orders of the magnitudes from this figure of the merits. Although the optical is going to stay here for the longer reach, but in IR lab, we believe if we can bring the optical to the in-package or onboard, we can actually save a lot of power and solve the problem that I was mentioning. Okay, to basically go to the optics, we have two solutions here I can show. Why the existing basically optical module solution cannot use for chip-to-chip communication. There are here 20 pluggable 100 gigabit per second module here, which is actually taking something like 3,000 millimeter square, and with a very, very high power. Of course, we cannot use that for chip-to-chip communication. But however, if we can combine all this and put them on a chiplet architecture, then we get actually to a solution that IR Lab has, which is a 2 terabit per second teraflops, and it's going to consume 75 millimeter square of the area, and at much, much lower power. This is our basically solution and architecture that we have. This is going to be actually a teraflops chiplet, this one, in a CMOS process. It's going to get packaged to a kind of XPU or a FPGA or any kind of ASIC, either on the organic interposer or advanced packaging. And then we're going to have our laser source as external from this package, which is again a teraflops, IR Labs basically laser source, which is, we call it supernova, which has a multi-wavelength laser source. What advantage do we get from it? First of all, is the low power, but on top of that, the reason that we put the laser outside is that the nominal actually operating temperature for ASIC these days is 80 to 110 degrees Celsius, which is not preferred for laser operation. In laser, actually, we prefer to keep it around 55 degrees. By doing this kind of architecture, we can decouple actually the thermal relationship between the laser and any kind of optical communication that we have. This architecture provides something like 3 orders of magnitude higher bandwidth density with 1/10 of the power and the latency of the copper at the distance of up to 2 kilometers. This is one of our recent demo where we had basically 2 large ASIC. You can see them here. Each of them packaged with the 2 IR Labs teraflops on that and 1 external laser source right at the left, which actually fits to the both of them. They don't need to be that close. You can see the test boards are kind of far from each other. And we showed an error-free, basically 1 terabit link between the 2 ASICs over 8 optical ports. These are basically the bathtub curves for 8 optical ports. Over the 8 wavelength with the energy efficiency of the 5 picojoule per bit. And we can actually go all the way to the 2 kilometers distance. We believe optical I/O will be actually part of the CPU sockets. In the past, we increased the number of cores to enhance the performance of the compute engines. Now people are actually going to the chiplet solution for beyond radical size to enhance and increase the performance of the CPUs. In general, basically, CPUs are many compute cores and functions wrapped in the power-efficient, low-latency, high-bandwidth interconnect, and that's the place actually we believe optical I/O can play a strong role because it has all these characteristics that I mentioned. Call for action, I think I'm going to basically help Bob you a little bit here. The ODSA BO meeting is going to happen every Wednesday at 9 a.m. And our spec of the BO is going to be released soon. And there is a wiki page here. You can go and find more information. And if you have any question, you can contact me or Boppy regarding the BO and ODSA or about the IR labs at my email address here. Thank you.